Okay, in this video we are going to talk about a special kind of trees called router trees. So we'll talk about the definition of the router tree and some of the terms related to router trees. So let me start by defining a router tree. So a router tree is almost similar to a tree, but here the difference is that we designate one vertex as a root and all the edges are directed away from the root. Okay, so let me write down the definition, then after that we will go through an example. So a tree in which one vertex has been designated as the root and every edge is directed away from the root. Okay, such a tree is called a router tree. So a router tree is a tree in which one vertex has been designated as what is called this root. So that is why it is called router trees, and every edge is directed away from the root. So it is kind of a directed graph. Okay, and we designate one vertex as the root and every edge is directed away from the root. Okay, let's consider this graph. Let's call this graph G. Okay, so here we can see that this graph is a tree. It is a connected cyclic graph, but it is not a routed tree. Okay, in order to make this particular tree a routed tree, what we do is we will designate one vertex as a root. Okay, so let's take this vertex F. Okay, so let's take this vertex F and designate that F as a root. Okay, so then after that what we do is, okay, once we fix the root, every edge is assumed to be directed away from the root. Okay, so we have a direction assigned to each and every edge in this tree. Okay, and the direction is assumed to go away from the root. Okay, so in this case the direction will be like this. Okay, so it's away from the root. Okay, away from the root like that. Okay, something like this. Okay, so let me redraw. Okay, this tree. Okay, such a way that this kind of representation is commonly used. Okay, so this root will come at the top, something like that. So if will be here. Okay, then followed by these adjacent ones. Okay, adjacent one D and J. Okay, so D is here, J is here, and we have these directed edges. Okay, and this is the common representation of a routed tree. Okay, F. Okay, and we have one more edge here. Okay, D, G, J. Okay, G is here, and this edge is directed in this way. Okay, so from D we have these two adjacent vertices B. Okay, B and D, and here the direction is in this way. Okay, from D, and from B we have these two A and C. A and C, and here the direction is in this way. Okay, and from E, okay, it doesn't have any adjacent one, right? Directed adjacent one. What about G? It has two, H and I. Okay, so H is somewhere here, I is somewhere here, and these edges are directed in this way, and J have these two adjacent vertices. Okay, so J, K and L, and the direction is something like this. Okay, so okay, this is a router tree, and here what we did is we took this tree and make that tree a rooted one by fixing this vertex F as the root. Okay, so this is a routed tree, and here okay at vertex F. Okay, so a routed tree is a tree in which one vertex has been designated as the root. Okay, so this F is designated as a root, and every edge is directed away from the root. Okay, so this is a router tree that is obtained from this one. Okay, similarly you can have many different router trees here. Okay, what we could do is we could fix D as a root, and we will get a different router tree. Okay, and all the edges will be directed away from that root D here. Okay, similarly you could have another router tree where this L is fixed to be the root. Okay, in that case L will be at the top. Okay, and we have other vertices okay below that, and all the edges will be directed away from this root. Okay, so this is one such router tree. Okay, and here the most important thing is that okay here we have a particular vertex called the root. Okay, so a router tree is a tree in which one vertex has been designated as the root. Okay, something like this, and every edge is directed away from the root. Okay, and when we draw a router tree, what we do is we normally omit these directions. Okay, once you are said that okay that particular tree is a router tree, then this direction is implicitly hidden in that representation. Okay, so normally when we talk about the router tree, we won't specify this direction. Okay, it is already implicit okay within the definition. Okay, so a router tree is a tree in which one vertex has been designated as a root, and every edge is directed away from the root. Okay, so let's look into some more terms related to router tree. Okay, so definition of what is called a parent, child, sibling, and a leaf in a router tree. Okay, so let T be a router tree. Okay, so let's consider this tree, and okay let's call this T a router tree, and since it is rooted, so we assume that this A is the root of this tree, and all these edges are directed away. Okay, something like this, directed away from the root. Okay, normally we won't draw with these directions if it is already implied in the definition. Okay, so this is our router tree, and okay, so let's define the parent of a particular node. Okay, child, sibling, and leaf in a router tree. Okay, so the parent of a particular vertex is defined as follows. Okay, if V is a vertex of this router tree T, okay, other than the root, okay, the parent of V okay, so we are defining the parent of a vertex V okay is the unique vertex U. Okay, it is a unique vertex U such that there is a directed edge from U to V. Okay, such that there is a directed edge from U to V. Okay, for example, let's consider this tree, and here let's fix a particular vertex, say L. Okay, so the parent of L, okay, in this case is, okay, the parent of L is the unique vector U such that there is a directed edge from U to V. Okay, so here we are dealing with a tree, so okay, all the paths will be unique. Okay, so the parent of L, we look for a directed edge that is coming to L. Okay, so we can see that we have this directed edge, right, from this vertex G to this vertex L. Okay, so that says the parent of L is G. Okay, similarly the parent of F here is, okay, the parent of F is C. So we have this directed edge, right? Parent of F is C, and parent of J is E. Okay, etc., etc. And here we can see that the parent of A is not defined. Okay, so the parent of A, which is the root in this case, okay, it is not defined. Okay, for other vertices we will have a parent. Okay, so the parent of a vertex is the unique vertex U such that there is a direct edge from U to V, and here, and this V is called a child of, okay, V is called a child of U. Okay, so in this case we call the parent of G, parent of L equal to G, and that says the child of G is L. Okay, and child of C is F. Okay, child of G is L, child of C in this case is F, another child of G is G, and so forth. For example, here the child of D is H, and another child is D. Okay, or we call the children of D in this case children of D in this case is, okay, these two vertices H and I. Okay, and similarly the children of A is B, C, D. Okay, so here we say that D is a child of A. Okay, since we have this directed edge from A to B. Okay, and that says A is the parent of B. Okay, similarly C is a child of A because we have this direct edge, right? And we also say that A is a parent of, okay, is the parent of C. Okay, so anyway the parent of a particular node will be unique in a router tree. Okay, so the parent of V is the unique vertex U such that there is a direct edge from U to V, and V is called a child of V. Okay, so this is how we define parent and child of a particular vertex in a tree. Okay, so let's define what is called the sibling of a particular vertex. Okay, so okay, this is called the child of V, and the sibling of a vertex is the vertices with the same parent. Okay, so the vertices are called siblings. Okay, so these are the vertices with the same parent. Okay, for example, if we consider this graph, okay, B, C and D. Okay, so here we can see that the B, C and D, okay, they are siblings because they have they have a common parent, in this case A. And similarly F and G, okay, F and G are siblings because F and G have a common parent. Similarly L, M, N, they are siblings. Okay, they have this common parent G. Okay, and this N and okay N and K, they are not siblings because okay they do not have a common parent here. Okay, anyway, okay. Similarly, O and P are siblings because they have a common parent. So vertices with the same parent are called siblings. Okay, so let's define what is called a leaf in a rooted tree. So a vertex is defined to be a leaf is defined to be a vertex with no children. So a vertex with no children is called a leaf. Okay, for example, if you look into this tree, okay, this J is a leaf, K is another leaf, O is another leaf. So okay, J, it do not have a child, right? They do not have children. Okay, so that's why okay these things J, K, O, P is also a leaf, M is another leaf, okay, N is another one, H is another leaf, and I is another leaf. Okay, and I think this is also a leaf. Okay, because it have no children. So a leaf is defined to be a vertex with no children. Okay, it is called a leaf. So if you consider this tree, this rooted tree, then these are leaves J, K, F, O, P, M, N, H, L. Okay, they do not have a child. Okay, and that says all these vertices are leaves. Okay, so let's define some more terms here. So internal vertex in a rooted tree. Okay, so let's see what is an internal vertex. So vertices okay, that are not leaves are called internal vertices. Okay, okay, so that are not leaves means okay those vertices that have children are called internal leaves. Okay, vertices that have children are called internal vertices. So for example, if we consider this tree T and A, suppose that A is the root. Okay, so okay, we always assume all these edges are directed away from the root. Okay, so normally when we draw a tree, okay, we want to give direction to these edges. Okay, that's implied in the definition. Okay, so vertices that have children are called internal vertices. Okay, for example, if you consider this tree, the internal vertices are okay, A, B, C, D, E. Okay, so if is not sorry, B is not an internal vertex because okay it is a leaf. Okay, so it do not have any children. Okay, so sorry for that. So internal vertices of this tree are A, C, D, E. Okay, if is not an internal vertex, D is not an internal vertex. Okay, H is okay, I is not, J is not, okay, K is not, okay, L is because L has a child here, M, right? L and M is not. So if you consider this tree, okay, all these vertices A, C, D, E, H and L. Okay, so these are internal vertices A, C, D, E, H and L. Okay, so vertices that have children are called internal vertices. So let's define what is called the level, okay, level of a vertex in a rooted tree. Okay, so the level of a vertex is defined to be the length of the unique path from the route to that particular vertex. Okay, so let me write down what I said. The level, okay, the level okay, the level of a vertex V in a routed tree is the length of the unique path from the root to the vertex V. Okay, so the level, level of a vertex is defined to be the length of the unique path. Okay, length of the unique path from the root to the vertex V. Okay, so for example, okay, here the level of A, it is going to be 0 because the length of the unique path from A to A is 0. Okay, and the level of this vertex C, okay, here is 1 because the length of the unique path. Okay, anyway, it is a tree, so by the definition of it, not by the definition, I think we proved a theorem in the last class, right? In the last video, that says every path in the tree is unique, okay, between every two pair of vertices. Okay, so the level of C will be 1 because we have this path, right, a unique path from root. Okay, so here we are assuming that A is the root here. Okay, and the unique path from A to root to C is this path, and the length of that path is 1. Okay, similarly the level of B, okay, level of B and level of D and level of E, okay, it is also equal to 1 because we can say that if you consider this vertex, okay, the path from A to E has a length 1, only this edge, right? Okay, so that says the level of these nodes. Okay, so these nodes, we have only one root, okay, it's all level 0, and this B, C, E, D, okay, these vertices are at level 1. Okay, similarly we can see that if we consider these vertices F, G, H, I and J, so here this unique path from root contains 2 edges, so the length is 2. Okay, so the level of these vertices will be 2, so these all vertices are at level 2 in this tree, and the level of K and L is, okay, in this case 1, 2, 3. Okay, and these two vertices are at level 3. Okay, and if you consider this vertex M, okay, and the level of M is the unique path from A to M is this one, A, D, D, H, H, L and L, M, right, and the length is 1, 2, 3, 4. So that says the level of M is 4. So this node, so this vertex is at level 4. Okay, so that's the definition of what is called the level of a particular vertex in a routed tree. Okay, so here, okay, all these nodes are at level 1, all these nodes are at level 2, all these nodes or vertices are at level 3, and okay, this M is at level 4, and normally root is at level 0. Okay, so this is how we define the level of a vertex in a routed tree. Level of a vertex V is the length of the unique path from the root to that vertex. Okay, so that's the definition of level of a vertex. Okay, so once we define the level, we can define what is called the height of a routed tree. Okay, so let me give the definition of the height. The height of a rooted tree, it is the maximum of the levels of the vertices. Okay, so height of a rooted tree is the maximum is the maximum of the levels of vertices. Okay, for example, let's consider this tree. Okay, we considered the same tree that we considered here. Okay, and A is the root. Okay, and the height of a rooted tree is the maximum of the levels of vertices. Okay, so here we have all these vertices and the levels are like 0, 1, okay, 1, 2, 3 and 4. Okay, we will take the maximum among these levels. Okay, so the maximum is 4 here, right? Okay, and that corresponds to this vertex. Okay, so that says the height of this tree. Okay, let's call that tree. Height of this tree, rooted tree, T is 4. Okay, so this is how we define a rooted tree. So in other words, okay, we can also say that the height, okay, in other words, the height of a rooted tree is the length of the longest path from the root to any vertex. Okay, so if you consider this tree and you consider the length of the longest path from the root to any vertex, okay, the maximum will be, okay, the length of the longest path from the root to any vertex will be the height of the tree. Okay, so in this case you can see that you consider the all the lengths. The longest one will be this one, A to D, D to H, H to L and L to A. Okay, and the length of that longest path is 4 and that says the height is 4. Okay, so that's how we define the height of a rooted tree. Okay, so let's see two more definitions. Okay, definition of what is called an ancestor. Okay, ancestors and descendants. Okay, descendants of a vertex in a rooted tree. Okay, so let me give the definition of an ancestor. Okay, ancestors of a vertex. Okay, the ancestors of a vertex other than the root. Okay, so that says the root, it doesn't have any ancestor. Okay, it doesn't have any parent, right? Okay, so the ancestor of a vertex other than the root or the vertices in the path from that vertex to the root. Okay, including the root and excluding that particular vertex. Okay, let me write down what I said. The ancestor of a vertex other than the root or the vertices in the path from the root, okay, to this vertex, okay, excluding the vertex and including the root. Okay, so what we do is we will start from the root and consider the path from root to that particular vertex. Okay, and we will collect all the vertices in that path, excluding excluding the vertex under consideration. Okay, so let's look into this tree and try to find the ancestor of one or two ancestors of one or two vertices. Okay, so ancestors of say L. Okay, so what we do is we will start from A and move towards L, and we collect all the vertices. So the ancestors of A, by definition, it includes the root A and all the vertices in the path from root to that vertex, excluding that vertex. So the ancestors of L, okay, it will contain L, it will contain A, okay, D and H, and similarly the ancestors of M will contain A, D, H and L. Okay, and say ancestor of G. Because what we do is we will consider the path from A to G here, and that, okay, in this case the path contains all these vertices A, C and G, and we include A and exclude G. So ancestors of G are A and C. Okay, so that's how we define the ancestors of a vertex. The ancestors of a vertex other than the root are the vertices in the path from the root to this vertex, okay, excluding that vertex and including the root. Okay, so similarly we can also define what is called the descendant. So the descendants of a vertex V are those vertices that have V as an ancestor. Okay, so the descendants are defined in this way. The descendants of a particular vertex V are those vertices that have V as an ancestor. Okay, for example, okay, if you consider this node H, okay, so let me write down the descendants of H here, or maybe descendants of G, okay, descendants of say D. Yeah. Okay, so by definition descendants of D are those vertices that have D as an ancestor. Okay, so we can see that if you consider G, okay, G doesn't have D as an ancestor. Similarly B doesn't have D as an ancestor. Similarly J doesn't have D as an ancestor. Okay, but we can see that if we consider this K, okay, K have D as an ancestor, so that says K is one descendant of D. Okay, and similarly if you consider this M has D as an ancestor. Okay, so that says M is a descendant, okay, of D. And similarly we can see that H and L, they are also descendants of D. Okay, so here the descendants of D are H, K, L and M. Okay, so descendants of D are vertices that have D as an ancestor. Okay, similarly the descendants of J here is 0. It doesn't have any other vertex as an ancestor, right? Similarly descendants of E are I and J, and descendants of C here is F and G, and descendant of A, okay, it contains all the vertices other than the root. Okay, so that is how we define the ancestors and descendants of a vertex. The ancestor of a vertex is the vertices in the path from root to that particular vertex. Okay, and it exclude the vertex and it include the root, and descendants are those vertices that have V as an ancestor. Okay. Okay, so let's look into one more definition. Okay, the subtree, okay, subtree of a rooted tree. Okay, so it is defined as follows. What we do is, okay, we consider a particular vertex and we include all the descendants, okay, and the edges, okay, incident on those descendants. Okay, that way we get a subtree of a rooted tree. Okay, so let me give the definition here. So if V is a vertex in a tree, then the subtree with this V as its root okay is the subgraph okay the subgraph of the tree consisting of all the descendants, okay, and V along with all the edges incident with those vertices. Okay, so is the subgraph of the tree consisting of V and all its descendants so all its descendants and all edges incident to these descendants. Okay, so this is how we define a subtree of a rooted tree. Okay, if V is a vertex in a tree, the subtree, okay, rooted at V, okay, with so subtree with V as its root. Okay, it means rooted at V is the subgraph of the tree consisting of V and its descendant and all the edges incident to these descendants. Okay, for example, let's consider this V to be, okay, this V to be equal to D. Okay, so what we do is we will consider D along with all the descendants. Okay, so D along with all descendants contains all these vertices, right? D, H, K, L, M. Okay, and all the edges incident to these descendants will give a subtree rooted at D. Okay, so if we said V to be equal to D, then the subtree rooted at D will look something like this. Okay, it will contain D, K, L and M and all the edges incident on these vertices. Okay, so I think D is somewhere here, so this will be H, D. Okay, so here what we did is, okay, we took this portion of this tree. Okay, so okay, a subtree rooted at V is the subgraph of the tree consisting of V and its descendants. Okay, for example, if you said V equal to D, okay, we consider all the vertices here that are descendants of D and along with D. So D, okay, D HKLM, and all the edges incident to these descendants. Okay, so this is a subgraph of this, okay, subtree. Okay, subtree of the rooted tree T. Okay, if you call this T, this tree as T. Okay, so here always remember, okay, this will be the root. Okay, so this is how we define the subtree of a rooted tree. Okay, so now some important definitions related to a rooted tree. Okay, so in the next video we will look at a special kind of rooted tree called binary trees. Then after that we will generalize the concept of two MRA trees. Okay, binary tree is a special kind of MRA tree. Okay.